Okay, hi everyone. How are you today? You hear me? Okay, thank you. So now it's time for lab 2. Okay, you submit the lab 1 last week, and this week is individual report. Okay, and now it's time for lab 2. So firstly, I will introduce about what you have on the canvas, the materials, the lab materials you have on the canvas. Okay, this one is the canvas side, and as you can see here, the first one is the lab note, and the lab note. This one is the lab note. This one is the most important thing in is the lab materials. Okay, in here you so use or the requirement. Okay, and the important equation. Okay, this one is the lab note, and this one you can download on the canvas, and if you have a look in it, you see today we have two parts, part A and part B. Similar to lab 1, okay, we have two parts, part A and part B. So we have the video for part A and video for part B. This one is for part A. Okay, you can have a look this one, part A and part B. And the data, this one is the data. Different with lab 1. Lab 1 we show you in the data in the table. Okay, but for the lab 2, we give you some picture here, screenshot. Okay, some screenshot. And at the end of this document, you can see the sample calculation. Okay, sample calculation for part A and the sample calculation for part B. Okay, part A and part B. And the last thing in the lab 2 you have is a recording with internal experiment. This one is a recording last semester. Last semester still online lab, but last semester I went to the lab and can show you the test reads, the instrument, the object directly. But this semester we can't do it because the lockdown and the restriction. Okay, so I will try to show you as much as possible using the material I have. Okay, and if you want, you can have a look in the recording last semester here. And about the recording of this semester, I will upload the recording maybe on tomorrow or on Sunday. Okay. Okay, about the materials you have in the lab 2. Do you have any question? Do you have any question about the materials you have? No? Okay. So do you know what is a wind tunnel? What is wind tunnel? And when we will use the wind tunnel? We use wind tunnel to test the effect of okay here. Yeah, the test of flow of fluid, and in this case airflow, wind tunnel airflow. The test the airflow and the effects of the airflow to the object. For example here, okay, we use to test the airflow to a car, a new car or airplane. Okay, this one is very big wind tunnel. Is the actual wind tunnel. Okay, we use to test because as you know, when we're moving, okay, we have airflow over the car, and when we have airflow over the car, we have force from the airflow applied to the car, and that's what we call is a drag force. Okay, we have drag force applied to the car. And do you know the Formula 1 cars? Formula 1 car, it can move faster because not only by the engine is stronger, it's because the force from the air applied to that car is smaller, and the force depends on the shape of the car. So the shape of the Formula One car is very important. Okay, shape of car is very important, and they will use the wind tunnel to test the effects of fluid flow on the Formula One cars before they create it. Okay, and in the experiment today, we will use the wind tunnel, a small one, to test the effects of the fluid flow of the airflow to some object like the cylinder, a square, diamond, and raindrop facing forward and upward. Okay, we will test it. It's similar to when we test a car or test an airplane. It's very similar, but our test system is smaller. Okay, and the accuracy is less than the when we want to test a car or an airplane. Okay, so firstly, we will have a look in the left note. The left note, we have this one is a left note. Okay. This one is the left note. Okay. External flow, wind tunnel experiment. External flow. And the fluid in this case air. Okay. Air. And the aim of the experiment. First one is to gain some experience with the measurements and methods relating to the fluid flow or relating to external flow. Okay. As you know, in fluid dynamic, we have two parts. Part one is fluid internal flow, and part two is external flow. Okay, internal flow is our left one. Okay, and external flow is our left two. Determine the pressure variation and different contributing components of the drag force on the common object, the circular cylinder. You have the circular cylinder like this. Okay, when air flow over this one, we will have a force F applied to this cylinder, and this force we call is a drag force. Okay. You obtain the drag coefficient for other object. Drag coefficient. You have the drag force equation of the drag force, F or D. I use D, that's easier. D equal to CD, the drag coefficient, 1/2 rho V square S frontal area. So an equation of drag force. So drag force will be depends on the drag coefficient. This one, CD is a drag coefficient. And of the other shape, this one for part B. Part B. In the part B, we have 5 shapes. We have a circle. We have the square, diamond, radar facing forward and facing upward. Okay. So this one is for part B. Okay. You find the drag coefficient for other shape, and you compare the results from the calculation of time here with as the result from elsewhere, from the textbook, the course note. Okay, so after the calculation, you find CD, the drag coefficient, and you will compare with CD you have from the textbook or the course note or the internet. You have, okay. Appreciate the flow phenomenon relating to circular cylinder and extension to other shape. This one for part B. Okay. And now I will introduce about the test rate or the test system. Yeah, this one is the test rate. We have this one is the wind tunnel. You can see this one at basement 4, building 11, UTS. Okay, you have airflow in as a big one here, in here, and go through a chamber. This one a chamber. In this one, we have the object instruments. The objects in here, and after that, it's go to a fan. This one, the fan. At the end of this system, we have a fan, and this one is a control box. Control box. We use this one to control, or we can control by the laptop. Okay, we can control by this one, the control box, or by the laptop. And now, what's inside this chamber here? Inside this chamber, or here, this one is in this chamber. This one is the chamber. Inside this chamber, we have airflow in here. Inside this chamber, firstly, we have a pitot tube. Pitot tube is this one. Yeah, this one is a pitot tube. Pitot tube. Okay, and in the pitot tube, you see, we have a different pressure transducer. And we have two signals here. One is total pressure, and another one is static pressure. And as you know, the total pressure is equal to static and dynamic pressure. Okay. So from this different pressure transducer, we have delta P will be equal to P total minus P static, or we will have dynamic pressure. Okay, so from the pitot tube, we have dynamic pressure. Dynamic pressure. And in this chamber, we have the test object is a cylinder. A cylinder. Yeah, you have this cylinder. And the parameter of cylinder here you have here. The diameter is 60 millimeter, and the length is 228 millimeter long cylinder. And in this cylinder, we have 21 holes or 21 pressure tapping on the half of the cylinder, top half of the cylinder. You have 21 holes. You can see this one. This one is a cylinder. And 21 holes you can see here. This one is hole 1. This one is hole 2. And hole 21 in the other side. Hole 21 here is the other side. We have 21 holes on the top half of the cylinder. Okay. And from one hole, you see the yellow one here, yellow line here. Okay. And we have another pressure, different pressure transducer with one signal from the hole. Or this one will be have P1 pressure inside the hole 1. Okay. And another one is free stream pressure. It means pressure inside this chamber. P inside this chamber. So from this pressure, different pressure transducer here, we have delta P1 equal to P1 minus P. Okay. And we have 21 holes. So we will have, you see here, we have 21 yellow line. You have this one, 21 from 21 holes. Okay. And one yellow one will be compared with the green one. Green one gives you the pressure in the chamber. This one will be compared with the pressure in the holes. So we will have 21 holes. So we will have this one is hole 1. It's hole 1. So to hole 21, we have delta P 21 will be equal to P21 minus P. We have 21 holes, so we have 21 different pressure transducer, and we have 21 pressure different delta P. Okay, we have 21 delta P. Okay, this one is the objects inside the chamber, and this cylinder will be used in Padai. Okay, in Padai. This one is the test rate. Do you have any question? Any question? Oh, good. Okay. Okay. So now is the parameters you take note of. Firstly, you take note the ambient condition, pressure and temperature. Okay. Actually, you can use the pressure is 101.3 kPa and temperature is 20 Celsius. That's okay. Or you can use the pressure and temperature from this one. This one is the screen source, the screen of the laptop. Okay. This one will show you all information, all data you need, all data you need. Okay. In here you see the room pressure and room temperature. Okay. Room pressure and room temperature. First one. And after that, you here pitot-static pressure reading. Pitot-static pressure is this one. Here. Pitot-static pressure. Or this one is dynamic pressure. You have this one from pitot-static tube. And this one show you the dynamic pressure. It means now in the chamber is as the fan speed is 1400. You have the dynamic pressure inside the chamber is 60.6 Pascal. In here you have set fan speed and actual fan speed. Okay, fast fan will be used to control the test rate. Okay, you can increase or decrease the fan speed by this one set fan speed. Okay, and for example, you increase the set fan speed to 1400, so the actual fan speed will increase until it's close to 1400. In this case, 1400.7. Okay, this one is actually, this one is set. Okay, and when you see the actual fan speed close with just fan speed, it means you can collect data. Okay, so pitot-static tube pressure you have here. Object shape, dimension, orientation. Okay, so the shape of the cylinder you have for the part A. For part B, the shape of other object you have here. As object in part B you have here. Okay, so the shape you can find on the left note. The location of the pressure tapping house on the cylinder surface. Okay, as I show you, you have 21 holes on the half of the cylinder. Okay, 21 holes on the half of the cylinder. You have pressure reading as this tapping house. Note that the reading is actually relative to the free stream pressure. Okay, we have 21 pressure tapping, 21 pressure tapping or 21 holes. So we have the information, we have the pressure at the 21 holes you see in the left hand side of the screen. You will see the 21 blue column. Okay. For example, for the column 1, this one is hole 1. For hole 1, you have this one is around, for example, 70 Pascal. It means you have delta P1 equal to P1 minus free stream pressure P equal to 70 Pascal. It means pressure inside the hole 1 is higher than free stream pressure inside the chamber is 70 Pascal. Okay. You see from hole 1 to around hole 5, the pressure inside the hole is higher than pressure in free stream pressure. Okay, but from 6 to 21 is negative. It means pressure inside the hole is smaller than free stream pressure. Okay, so based on this figure, you can find pressure inside 21 holes. From this one, you can find P1. Okay, vessel inside 21 house. This one, okay. This step pressure reading as this stepping total force and fan speed. Here you have, yeah, total force or drag force. This one, total force 1.05 Newton and fan speed 1400. Okay, is what you have in the screen. On the screen, you have everything. All data you need, you can see in the screen. Okay, do you have any question? Do you have any question before we coming to part A? No. Okay, so part A, we start with part A. Yeah, part A. For circular cylinder with pressure tapping, 21 pressure. Oh, what's the problem? Have 21 pressure tapping or 21 holes. Okay. And yeah, you will use this data set with table to collect data for part A. You see here the ambient temperature, ambient pressure you have on the screen, or you can use 20 Celsius or 101.3 kPa, that's okay. And you see 5 fan speed, but actually for the lab 2, you only choose 3 fan speed. You will choose 3 fan speed or 3 data sets for the lab report 2. Okay, 3. For example, you can choose 14, 16, 1800, 3, that's enough. Photostatic tube pressure on the right hand side of the screen. Okay, the force. And this one is the pressure in 21 holes. For example, we have the tube 1. We have is delta P is 70 Pascal. For things like that, you push in here, value in here. For the 16, you have here. 18, you have here. Okay, so you will have 3 set of data at 3 fan speed for part A. Okay, this one is a and what you have to do is 5 step here. You find pressure drag, friction drag, Reynolds number, drag coefficient CD, and compare CD from the experiment with CD from elsewhere. You have 5 steps. Okay, and in this lab note, give you some instruction here. For example, here this one. For this one is the cylinder. Okay, and this one is hole 1. This one is hole 21. Right? And A, B, C, D, E, F divide this half cylinder into some area. And in here you have equation to find the drag force between A, B, B, D, D, F. Okay, for example, yeah, you have all the main equation in this lab note, or you can based on the sample calculation. Yeah, in here I give you the sample calculation. We give you sample calculation because the airflow or external flow, you only study this one on week 11. On week 11. And as I remember, so you have to submit the lab reports on week 11. Okay, so maybe you can have look this one. Okay, you have look this one to know how to find drag coefficient, how to find drag force. Okay, because if you wait until week 11, maybe not enough time to finish the report. Okay, for part A, okay. This one using the data with the fan speed 1800 RPM. Here, this one is 1800 RPM, is this one. This one is 14, 14, 16. And the sample calculation use the data in this figure. Okay, 1800 IBM. And here is how to find a pressure drag and pressure in the 21 holes. Okay, you can here you give you some equation to find the small area. Okay, you equation to find dF. Equation here, some equation you can see here, or and you will have this table. This one is 21 holes. Okay, and because 21 hole in a half of the cylinder, so if hole 1 the degree is 0, hole 21 will be 180 degree, the angle from the front. Okay, and in here you will have the area, the corresponding area. How to find area? You can see the here in this one, the small area. Okay, so for the hole 2 to hole 20, the area will be like this. For hole 1 and hole 21 is a half. Okay, because the streamer tree. And this one is the pressure reading from you have from the blue column. You have here from the blue column. Okay, and when we have pressure, we have pressure force. This one is the force. Pressure force equal to pressure times area. We have this one. And from pressure force, we have the drag components. Okay. And from pressure force, we have total pressure drag. Total pressure drag equal to 2 times this number. 2 times this number because of the symmetry. All information you have in this table is from a half of the cylinder. Okay, so for whole of cylinder, you have 2 times. This one is the pressure drag applied to the cylinder. But as you know, you have the drag force will be equal to pressure drag by pressure and drag by friction drag. Drag by pressure different, and drag by friction between the airflow and the surface of the cylinder. Okay, so drag force, total drag force will be equal to pressure drag and friction drag. Pressure drag you have from the table here. Total drag is what you have is the screen from the figure from the picture. So you will have the friction drag. Friction drag will be equal to total drag minus pressure drag. You will have this one is a friction drag. Is a step 1 to 3. Okay, to here you finish step 3. And step 4 is you have to find the drag coefficient CD. And CD, we have the equation equal to total drag force divided by 1/2 rho V square S frontal area. Equation. With drag is total drag. This is total drag. Rho is the density. V is velocity. Velocity, air velocity you can find from dynamic pressure, or pitot-static tube pressure. Okay, this one from dynamic pressure. Sorry, V from dynamic pressure. And S frontal area, you have the cylinder like this. With this one is D, this one is L. Okay, so you see this from the side view, you will have the frontal area is DL, is a rectangle. So the frontal area will be equal to D times L. The area equal to D times L. That's easy, huh? So D you have, density you have, velocity you can find from dynamic pressure. Okay, yeah, this equation to find velocity from the hydrostatic pressure or dynamic pressure. Okay, and throttle area from the shape of the cylinder. So you can find CD. For example, you have CD is 1.21. Okay, 1.21. And now you will compare with CD from the textbook. And to find CD from the textbook, you have to know Reynolds number. Reynolds number. Here, this one is a figure used to find CD. For example, here you have the Reynolds number if 52,400 is around here. You will have in here, you will have CD. This one is CD from the textbook, is around 1.2 to 1.3. Okay, so we will compare this one with CD from the calculation. Okay, we compare, and you give the reason of the difference. You can discuss about the maybe its application, the possible application, the reason of the difference, or something to improve the experiment. Okay, this one is for part A. Do you have any question for part A? For part A, do you have any question? Nope, all good. Okay. So for part A, yeah, part A. We finished part A. For part B, for other objects, including circular cylinder without pressure tapping. Okay. So for part B, we will use, let me show, I show you, I show you this one. Do you see this one is the chamber? As a chamber, this one is a hydrostatic tube, and this one is the cylinder. Okay, and at the bottom we have, you see 3 objects here, 2 blue one and 1 gray one. Yeah. And for part B, we will use the object, 3 objects here to cover the cylinder. To cover the cylinder. Okay. For part B, we have here for part B, we have 5 objects here. Okay, let me see. Okay, here. For part B, drag force on different objects. We have circle, square, and diamond, raindrop facing forward, and raindrop facing backward. We have 5 objects, and we have to find drag force as a drag coefficient on 5 objects here. For first one, the circle. For the circle, okay, we will use the first blue object here to cover this cylinder. And when we cover it, we will have a new cylinder. New cylinder. This one. Okay, we will have a new cylinder. Okay, we use the blue one to cover the cylinder. And now we have a new one, a little bit bigger, and no pressure tapping. No 21 holes. Okay, that's why you can see the title is with circular cylinder without pressure tapping. Okay, now we have a new cylinder, the diameter is a little bit bigger, and no pressure tapping. Okay, this one is for a circle, the first object. Second one is square. Is this one square? Okay, we use the second object to cover the cylinder, and now we have a square. Okay, No, this one. This one is a diamond. Use the same objects, but we change the direction. We change the direction. We will have the diamond. Okay. And raindrop facing forward. Okay, raindrop facing forward. We use the gray one to cover the cylinder. Okay. And airflow from the right to the left, we will have raindrop facing forward. This one is raindrop facing backward. We change the direction. Okay. And we will have raindrop facing backward. You see the arrow here is airflow in this way. Okay. Arrow. So for part B, we have 5 objects. Okay. We will have 5 objects. We will have a cylinder with the length of this cylinder is the same with the length of the cylinder in part A is 2s millimeter. Yeah, the length of the cylinder is the same with the length of the cylinder in part A. For the square, we have a square with the length 228. L we have is 64 here. The diamond. Oh, what's the problem? Diamond. Oh, what's the problem? Okay, the diamond. Okay, we have the diamond. Airflow in this way. Raindrop facing forward. Okay, airflow in this way, and raindrop face backward. Okay, with the length of the object is 228 millimeter, the same length with the cylinder in part A. 5 objects, and in here similar to part A, we have in this table we have 5 speed, but you will choose 3 fan speed only. 3 fan speed, that's enough. Okay. X object, you will use the data at 3 fan speed. Okay. And the data here for part B. Part B. First one is circular cylinder. Because we, as you see, we use the blue one to cover the cylinder. Okay. When we cover the cylinder, we cover 21 holes. Okay. So you see the screen. The pressure on the 21 holes, same level. And negative. It's negative because now in the 21 hole, we only have static pressure because it's covered already. Okay. And that's why this pressure is smaller than free stream pressure or pressure in the chamber, because pressure in the chamber equal to static and dynamic pressure. Okay. So based on this one is the pressure is the 21 holes. But for the part B, when we cover 21 holes, you can ignore the information in the left hand side is the 21 holes, in the 21 blue column. You can ignore this one. We don't use the 21 holes. We only use the data on the right hand side, this one. Okay. We use room pressure and room temperature. We use the total force or the drag force applied to the cylinder. We use a pitot-static tube or dynamic pressure. Okay. And we use the fan speed. It's the right hand side only. Okay, you ignore the 21 blue column. Similar for here, 1600, you ignore this one. Use information in the right hand side. Okay, You ignore this one. Use information in the right hand side. For part B, with each object, we only give you the 3 picture at 3 fan speed. For example, for circular cylinder at 14, 16, and 18. Okay, it means you have to use all of them because you have to choose 3 the data at 3 fan speed, but we choose for you already 14, 16, and 18. Okay, because the wind tunnel is long time ago, and if it's run at too high fan speed, it's unsafety. It's not too safety. So that's why we only collect data at 14, 16, and 18 RPM for you, and you can use all of them. For the square, similar. Ignore left hand side. Use the data in the right hand side. Ignore this one. Use the data in the right hand side. Okay. You in the right hand side. So similar for diamond. Okay. Similar for raindrop forward. Okay. Use data in the right hand side and raindrop backward. Raindrop backward. Okay. And at the end of this document, you have the sample calculation. The sample calculation for part B. Okay. Yeah, it's a test step by step for part B. Okay, so for part B, you do only step 3, 4, 5. 3, 4, 5 only. You don't have to do step 1 and 2 because step 1 and 2 is for 21 holes. Okay, you find pressure drag in the 21 holes and friction drag in 21 holes. But for part B, we cover 21 holes already, and we don't use the data in 21 holes. So that's why for part B, you want to do part 3, 4, 5. You find the Reynolds number, you find the drag coefficient CD, and you compare CD from experiment with CD obtained from elsewhere. That's enough. Easy. Okay. And we have the sample calculation for part B for you here. This one, part B. Okay. The equation is similar. We have drag coefficient CD equal to total drag force divided by the density divided by 2 times velocity times S frontal area. This one is for square shape. Square shape. Okay. With velocity as speed, you have from pitot-static pressure. Yeah, from pitot-static pressure. Okay, you find velocity. Density from air properties. Drag force from the picture. Okay. And S frontal. S frontal is similar. You have S frontal for this one is for cylinder. Okay, I draw here for cylinder with the L. S frontal will be equal to D times L. For square, use airflow in this way. Okay, so this one is D, this one is L. S frontal is D times L. D times L. For the diamond, airflow in this way. This one is D. This one is L. But now S frontal is not D times L. Will be equal to D1 times L. With D1 equal to D times 2 square root. Okay. D1 times L, not D here. So, okay, this one is frontal area. But it's going to be different for drain drop. It's going to be different for drain drop. For drain drop, you can have a look in lecture 11 slide. Drain drop or airflow or thin body. Okay, CD for airflow or other thin body will be based on the platform area rather than the frontal area. Okay, will based on. So S frontal in the equation will be replaced by the platform area. Okay, and platform area is when you see from the top view. Okay, and you see this this one will be a rectangle, which one side is L, and another side is the length of the airflow. Okay. So for you have brain drop like this. Okay. With this one is D. This one is L. This one is B. Okay. So you see from the top view. So S platform will be equal to B times L, not D times L. It's B times L because it's from platform area. Platform area when you see from the top view. Okay. Frontal area when you see from the side view. So for raindrop facing forward and backward, you use platform area. Okay, this one will be replaced by platform area. Process the same. So use this equation. Everything you have, drag force you have, density you have, V you have, S frontal or at platform you have. So you can find CD. Okay, you find CD and you compare with CD from the textbook, course note or something like that, or from internet. It's similar to Padai. Okay, similar to this one. Okay, you compare. Yeah, you compare what you have from the calculation is the what you have from the textbook. Okay, do you have any question? Do you have any question? Okay, so good. And in here, in this document, the last note, okay, we give you some suggestion for discussion here, point for discussion. Some point you can use in the discussion. Okay, you give the comparison between CD from the calculation and CD from and the other valuable information from the textbook or from the internet. Okay, and you give the relevant of the experiment to the subject, to everyday's life work, to possible future works, things like that. Okay, you can give the comments on possible application, or you can give suggest some ways to extend or improve the experiment. There's some points for discussion. Okay, you can base on this one, or you can discuss more than this one is okay. Whatever you want. Okay. And in here you have still have some equation, but all equation you need you can see in the sample calculation. Okay. Let me see anything. Any question? Do you have any question? And please have a look the video on the canvas, because now, as you know, I can't go to the UTS to show you the wind tunnel directly. But in this video, I created maybe 1 year ago, okay, as a lab. Okay, this one is wind tunnel. Okay, so this one is a laptop, airflow on this way, and at the end you see the gray one is a fan. Okay, and in here I show you everything, including this one, the control system. You have you see you have a two mode, is a PC mode and a local mode. Local mode is mean you can control the speed by using this one, speed control. Okay, or we can control the speed by the laptop. This one is a speed, it's showing the small screen. Okay, or we can use a laptop here, this one, to control. We control by enter the number at the set fan speed here. You can increase it into for example 400 for 1400, okay, something like that. Yeah, and I show you a little bit about the test rate, the instrument, the objects we have. Okay, and here you can see 21 holes. Yeah, 21 holes on a half of the cylinder. Okay, with one hole we have one yellow line. From the yellow one we have the pressure inside this hole, and this one will be compared with free stream pressure. Okay, and so use the data. Yeah, the data, we run it and we have the data like this. This one is part A, and part B. You can see here, this one is for cylinder, and besides this we have two other objects used to cover the cylinder. Okay, yeah, where, yeah, okay, for example here we have the first one is for circle, the second one for the square and diamond, the last one for raindrop facing forward and upward. Okay, and now here we will use this one to cover the cylinder, easy. And we have a new cylinder and airflow from right to left, okay, to the new cylinder. When we cover this like this, we don't have 21 holes. Okay, no 21 holes. Okay, so that's why I said we can cancel, we can ignore the information in the 21 holes. Okay, and similar for other one, similar for okay, you can go now. Yeah, that's finished. I just only show you some extra information. Okay, and the drag force, as I said, is very important, because here, if you have looked in here, this one you have this one for the drag force for some car, you see, and we have this one from wind tunnel experiment. With this kind of car, for example, Fiat Balilla, for example, drag coefficient CD is 0.6. Okay, but for some sport car like this, the drag coefficient is only 0.3. Okay, 0.3. The drag coefficient higher, it means the drag force is higher. When drag force is higher, it means air resistance is higher. It means we need more energy. We need more fuel. Okay, drag coefficient higher, it means we need more fuel, more energy. Okay, this one for sport car. That's why for the sport car we can go with the higher speed. Okay, high speed. Okay, you have any question for me today? Any question? Zaki, any question? Oh, good. Okay. If you don't have any question, thank you. See you. If you have any question, you can ask our tutor or you can email me. Okay. Yeah. Thank you. Bye bye.